I'm going to continue to talk about this Buneman graph, actually Buneman tree, and this will be my last video on this paper. Basically, I'm going to complete the proof of this theorem 2. It's saying that like if we have a kind of like a metric like D, it's like a lateral distance D, or like they call it the similarity coefficient to describe distance between all the points, and I will have this kind of induced addictive metric like delta D, and that D will be equal to delta D if it satisfies this 4-point condition. So of course I need to specify what is the 4-point condition first, and also maybe a quick review of like what basically what we have. So we have this Buneman construction, and we had several videos basically show that like okay, any tree can be constructed with this Buneman construction, and also like I guess like the first video is basically trying to show the Buneman tree. It's not the first video, maybe the second video, trying to show that the Buneman tree is in Buneman construction. We introduce a tree, and then we kind of show that okay, all tree can be constructed using this Buneman tree. So then we can use this Buneman construction as a tool to show different characteristic of tree. So we showed last time is a theorem basically saying that like if we have some addictive metric, let's say we have a tree, and we have this additive tree metric. Actually, addictive in the sense we're thinking of like if we look at distance between two nodes here, then the distance of these nodes would be like this distance at this distance and at this distance, something like that. If I have an additive tree metric, we showed that last time that if we know the distance between all the nodes, then the whole tree topology is specified. So this time like we want to show this theorem 2 there, like we show that okay, we have this lateral distance of like two member of the set, base set. I guess I still should give a quick review of how the Buneman construction. So basically, I call it Buneman construction, but how he had, or Buneman representation maybe. So it trying to build a tree with the following components. Basically, first introduce a base set, like let's say 1, 2, 3, 4, and so on. Okay, I guess I use the path graph again as an example, and then like I will have some split of this set. Let's say I have a first split sigma 1 that split the set into 1 and 2, 3, 4. Let's say. So, and I have like sigma 2 trying to split that into 1, 2, and 3, 4, and I have first split trying to split it into like 1, 2, 3, and 4. So then basically like a node for the tree basically is will be, maybe I call this use my previous notation, that this can be like S10 and S11, this two set. This is S20 and S21, this S30 and S31. Now, so for a node of the tree, is like I'm going to pick a subset out of the tree. So pictorially, I can describe like this: 1, 2, 3, 4. So I will pick like for the first split, I will pick the first subset. Let's say I pick 1 here, S10 here, and then for the second split, I pick this one, and for the third split, I pick this one, let's say. So this form a node, and this node will connect to another node. So and of course I will connect to another node. Will connect to another node that only differ with one subset of the splits. So more precisely, let's say I have 1, 2, 3, 4 here. So I only change the first split here, like instead of like taking like the subset 1, I take the subset 2, 3, 4. So and the rest is the same. And then like these two nodes will be connected by the I can indicate the edge by the split there, like sigma 1, let's say, and so on and so forth. So I can have two other nodes. So I can, for the next node here, I can change, like let's say the second split. So I can change to this one here, this one here, this one here. So I have similar to, and then 1, 2, 3, 4. Okay, different colors. I guess it's fine. So finally, I instead of like having this one, I can have like this. Okay, this differ by similarly. So so I have 3 in this case. So you see that like with the base subset and the split here, I specify the a tree here, and for the base subset, like we can introduce some for each members, or actually each pair of members from this base set here, base set S here. We may have some lateral distance that D here. We can describe, for example, like for member like 1, 2, the distance is just 1 minus 2. Let's say I can pick any distance. Maybe I pick a distance like that. Actually, I mean, like, okay, when I say I can pick any distance, I should be careful, because the distance, how you pick the distance, will induce the structure of the tree. So, but actually this distance is fine. It will I think it will turn out to be this graph, this path graph, as we have here. So, and so I have this distance is the distance of like any 2 points here, but I want to have a kind of distance between nodes, and very kind of reasonable distance would be like for each of the sigma here, I will assign a distance for that. Like I assign some like mu1, mu2, mu3. So then if I distance of nodes will be just like sum over all these mu's here, right? So more precisely, it's like if I have 2 nodes, like let's say I have delta star, I call it m1 and m2. That's basically distance of the 2 nodes will be sum over all the sigma, basically all the splits in that tree, such that I have mu sigma and delta star sigma m1 and m2. So my delta star here is saying that like if from m1 and m2 there's a transition for the sigma, so basically like m1 and m2 pick 2 different subsets from the sigma, so then I should add that. So for example, like if I go along from here to here, then I look at the sigma, there's a change of like sigma 1 here, so therefore I should add mu1 here. But on the other hand, like from this node to this third node here, if I look at sigma 4 is off, sigma 3 here, apparently there's no transition here. It's not, I mean, from the first node to the third node, I won't go through the transition of sigma 3, so therefore I shouldn't add like add mu sigma mu 3 there, or mu sigma 3 there. So maybe I give an example, like for example like delta star okay, I mean this first node here and this third node here is equal to mu1 plus mu2, something like that. But okay, let me just erase that. This is not very. So we also mentioned that like we can have like another measure, because like if we compute the nodes of like two of this distance here, I mean the additive metric of like two nodes here, a more oftentimes like a more convenient way to find it is like, let's look at the support of each the node. So the support is basically I have all the subset in the node here, and I take the intersection. If let's say I have A and B, a subset of support, support of like M1, and support again is like the intersection of all the subsets in N1, and B is the support of N2. Then if I define a similar metric that is sum over mu sigma, but I have this delta sigma AB instead, where this delta sigma is saying that like if I have the sigma is separating A from B, so then in that sense like these two metrics will be identical. For example, what I mean is like if I have A is in support of N1 and B is in support of N2, then these two will be the same. And it's often like much easier to work with like this delta AB instead of this delta star M1 M2. And also like we talked about like last time, like we try to induce the mu sigma from D here, and a natural way to do that as proposed by Professor Buneman is like I can have like mu sigma as a 1/2 minimum pick order A, B, C, D such that A, B, C, D in S such that A, B separate or like sigma separate, I should say sigma separate A, B from C, D. Then I have this is like D, A, C plus D, B, D minus D, A, B minus D, C, D. So if I define this mu sigma as this, and then of course my delta then here will depends on how I define the D. Then it's probably better I have a kind of like use a subscript here just to indicate that my delta this metric here is induced by D here. So I have delta AB is equal to this mu sigma basically. I have used this mu sigma. And we show that like we have some lateral property. Basically one property is that like if we have this delta D is an induced metric from this D here, then for any AB here we'll always have like delta DAB will be less than equal to DAB. That's from the, I think it's like less than, okay. It's from Lemma 9 in that paper there. Yeah, so it's like this one here. Now as we said, like what we're interested in is like to complete the entire paper. That's the another major result, but yeah, another major result of the paper is like you want to show that like under some condition these two will be the same. So it will be the same when the distance, the lateral distance that we pick satisfy this 4-point condition, they call it. So the 4-point condition is basically actually I maybe it's easier, I can show it pictorially. Let's say if I have like A, B, C, D, so I have like these points here. So the 4-point condition is saying that like okay, my distance, maybe I put AB here, A, B, C, D here. My distance, like distance AB plus distance CD will be less than equal to the maximum of DAC plus DAB BD and DBC and DAD. So this is like known as this 4-point condition here. So this 4-point conditions. So actually, I'm not going to show it here, but like the 4-point condition is like I think it's a necessary and sufficient condition for your distance metric is kind of like addictive. Because like as you can see here, like my 4-point condition is basically saying that okay, if I have AB here, like I have the distance here, so I have distance here AB here, and if I add the distance CD here, what I'm expecting is like okay, if I have my points is like assigned like this, I would expect like AC like this one here will be the same as like BD here, basically like this sum together like AC plus BD will be equal to this AB plus CD. So therefore AB plus DAB plus DCD will be less than equal to DAC plus DBD. And of course it depends on how I assign these like labels. There will be other situations. So therefore like that's also like taking into account like I have like another one is like at DBC and DAD. So for example like if I have to know instead like let's see, yeah, I don't know how to assign, but anyway, so what I want to say like this is actually kind of equivalent to like the addictive tree matrix. So it's like if it's a way to show to kind of like verify that like whether your metric is like addictive. So it's kind of like, so therefore like the theorem 2 is basically saying that like if your metric is addictive, then the induced metric will be equal to your D precisely. So so it's kind of reasonable because like your induced metric itself is like addictive, right? So then I mean by construction, your induced metric is supposed to be addictive. So therefore like if your original kind of like metric is addictive, then you will kind of like intuitively kind of expect that these two will be overlapping each other, so they will be the same. So but we will give a more kind of rigorous proof on this one. And before I go into the proof, let's give also another remark for another metric. Let me just erase some where like to get some space here. So maybe I can erase this one here. So I'm not sure I should erase this. So anyway, let's also mention this like called ultrametric inequality. Oh, actually, by the way, like before I go further to this ultrametric inequality, I forgot to mention one thing. For the 4-point condition, that when it's satisfied, one can see that this is also like a condition help us to verify this the metric should be like it's a metric, kind of like you. Okay, it's probably not sufficient to say. Okay, what I want to say like this 4-point condition also will imply the triangle inequality that is required in metric. Triangle inequality, as you can see very easily. So for example, like the triangle inequality is saying that like if I have DAB, it should be less than DAC plus DCB, something like that. I will have this immediately if I pick, for example, C let's see, C is equal to D, right? If I C equal to D, this will be gone because like the distance from itself is the same, will be equal to 0. Then this will be DAC plus DBC, so that will give me this one guy here. And for this one, is DBC plus DC is the same thing. So this 2 times is the same. So it's like I'll have this triangle inequality. Okay, let's go back to this. I want to finally mention this like ultrametric inequality. This ultrametric inequality state that like if I have like 2 points, actually 3 points, like A, B, and C, I have it's kind of like similar to this triangle inequality, but it's quite a bit more stronger. So it's saying something like I want DAB is less than equal to DAC and DBC. And actually, like if you let's see, maybe I can let's see if I can draw something. Let's see if I can draw something. I think this is like one of these plots that used to illustrate whether your metric satisfies this ultrametric inequality. For example, like if you have ultrametric inequality satisfied, you will want to have like graph not like this, but more like graph will be like this. So I will go down to have like equal depth. So for example here, like if I have something like that, if I look at DAB here, let's say if I have AB here, let's say AB is here, let's say I have a C here, then DAB, you see is like apparently is much longer. I assume like I'm using this distance, like I mean the length here also like can't represent the distance of the path there. So I have DAB is much longer than like DAC plus DBC, something like. So on the other hand, if I have a tree that each node go into the equal depth, then I have DAB C here, DAB here will be the same as like DAC and I mean the maximum of DAC and DBC, or like it will be less than like the maximum of DAC and DBC. So what we have is like this ultrametric inequality is quite a bit stronger, and pictorially you are kind of like can think of like you will be seeing tree, something like that. But actually one can also show that, but I'm not going to show it here. Is that for the ultrametric inequality, when it's satisfied, it will ensure the like 4-point condition as well. But since I'm not going to use it, so I'm not trying to kind of show this one. So now let's go into the theorem again. So the proof of the theorem. So basically, if I have as I said, like we are kind of expecting like if the tree is addictive, or in the sense that if the 4-point condition satisfied, then like delta D will be equal to D. So and again, like from earlier lemma, we already know that like D is bigger than equal to delta D. So therefore we just need to show the other inequality. And also like this is like a sufficient and necessary condition. So basically, or maybe like let me have a new, yeah. So let me just write down the theorem again. So the theorem is saying that like I have del D is equal to D. So if and only if D satisfy the 4-point condition. So so it's a if and only if statement. So let's try to show it like one way at a time. Let's try to show the forward way. So basically, like we want to show if like del D is equal to D, we want to show that the 4-point condition is satisfied. So, and let's say I have 4 points here. I have 4 points, like A, B, C, D. And I depending on the tree here, like if I have the base set that contains like these 4 members A, B, C, D. Note that like okay, I guess I didn't mention in this video here, but for the split, to actually construct a tree instead of like arbitrary graph, we need to make sure the splits, they are all compatible with each other. So in the sense that the split has to satisfy this condition that like I have like split is like let's say the first split is S10 S1 1, and then I have a second split. This is sigma 1 here. I have second split like S20 S2 1 here. The second split here. I need to make sure that one of the subset do not intersect. For example, I have S10 intersects S20 is not, is equal to an empty set. So we need to make sure that, so, and this also actually implies that like one of the subset from one space should be like a okay. Yeah, one of the set in one space should be a subset of another split. So for example, like I will have like one is like sigma 1 here. Oh, better. So sigma 1, let's say this one, and then like this is sigma 2. So this is valid. So because in this case I will have this let's say A here is S10, and the complement, okay, I can, oh yeah, I just consider this subset A here, and the complement of this west subset here, I have BD here, right? So BD and A will not intersect. So therefore, like it's a compatible. These two are compatible splits. So, however, like if I have, let's say AB and CD, if I have something like that, then it's not compatible. So apparently, like no matter how I'm going to do it, which whatever subset I selected from each of the split, they will have like non-empty intersection. So now therefore like that will be like basically let us start with we say we have 4 points A, B, C, D here, and the 4 points, any 4 points A, B, C, D, like because I want to show the 4-point conditions, right? So I let me arbitrarily pick 4 points A, B, C, D, and A, B, C, D like can either have I can either have like A, B kind of like have some split that kind of encodes A, B at the same time, or I can have like split encodes like AC at the same time, but I cannot have like both happen at the same time. So but without loss of generality, let's say I consider like AB, so maybe I can try other cases like, yeah, actually let's case 1. It's like I have like some sigma in the tree kind of separate AB from CD, and let me denote lambda AB as, actually I used this notation before, so in the other proof, lambda AB is the sum over all the sigma, mu sigma, and we remember like we have this delta D is defined as like this sigma sum over sigma in T mu sigma times delta sigma, yeah, and this is like basically the mu sigma there, and sum over the mu sigma that like sigma for all the sigma separate AB from CD. So um, uh, so and okay, let me write it down first. The other thing. So for example, like and yeah, and let me denote also like lambda a as like something similar, that sum over mu sigma, that sigma separate a from b c d. And similarly, I can define like lambda b is the same thing, lambda b as but like b separate like a c d and like lambda c and so on. And note that there's no need for me to define lambda AC or like lambda uh, AD, because we know that like once I have like some sigma separate AB from CD, I cannot have some sigma like separate AC from BD. So basically I only have these 4 cases here. Well, not 4, there's actually 5 cases here. I also have lambda D here. Now then, because I have this assumption here, delta D is equal to D, then I will have like DAB plus DCD, so it's equal to delta DAB plus delta DCD, right? Now what is delta DAB and delta DCD? So like if I think of like delta DAB, delta D is this guy here, right? So I should sum over all the sigma separate A from B. So stuff that's going to separate A from B is basically like lambda A plus lambda B, right? And because this is basically all the sigmas that all the mu sigma with sigma separate A from B, C, D, and this of the mu sigma that with sigma lambda B is a sum over all the mu sigma with sigma separate B from A, C, D. So okay, this I think this should be quite easy to see. So and then like delta D C D will be just like lambda C plus lambda D, right? Okay. So I can do the same thing like lambda AC, therefore plus lambda B, sorry, not lambda AC, I'm sorry, DAC plus DBD, and by the same token, AC will be equal to, now here I need to be careful, like the sets that's going to separate A and C, there will be like lambda A and lambda C here, but also lambda AB will also separate A from C, right? So I should have lambda AB as well, and this will be lambda B plus lambda D and plus lambda AB as well. And similarly, I will have like D AB plus DCD is let's see, AB and DCD will be equal to lambda, lambda A, lambda C, I already did that, I guess. Actually, from that, it's already be okay, because for this case, I already satisfy this 4-point condition, because the 4-point condition is like DAB plus DCD is less than equal to maximum DAC plus DBD and DBC plus DAD. And of course, because all the mu sigmas are positive, bigger than equal to 0, bigger than 0. Therefore, like lambda A, lambda AB and lambda ABCD also are bigger than equal to 0. So, and therefore, like I will have lambda AB bigger than equal to 0. Therefore, like this is bigger than this. So I already have this here. So this one is bigger than this. So for this case here, so it works. So yeah, I will try one more case. So we theoretically should consider like all 4 cases. So A B, AC. Like for tree that have sigma that separate AC from BD, and for tree that separate from AD from CB and so on. But let me just do one more. Like let's say if I have case 2, it's like I have some sigma separate AC from BD, So, and for this case here, instead of like lambda AB, I have some lambda AC. It's just with the same token, defined in the same token, basically, will be sum over all the mu sigma, such that like sigma separate AC from BD. And for the rest, lambda A, lambda B, lambda C, lambda D is defined in the same manner. And so then like again we can do the same check here. So I have like DAB plus DCD. So in this case will be equal to lambda A plus lambda B plus lambda AC plus lambda C plus lambda D plus lambda AC. And DBC plus DAD is equal to lambda A. Again, lambda AC plus lambda B plus lambda C plus lambda AC plus lambda A plus lambda D, right? So basically lambda A, B, C, D, they have all, and then like plus 2 lambda AC. So these two are basically the same, right? And again, like this is actually sufficient to show the 4-point condition already. So we see that like this, therefore this term here, the first term is actually equal to this one, is basically therefore is less than the maximum of like DBCAD and DACBD. And we can also verify like AD from BC, but I guess I'll skip it because it's totally the same. Now let's try to show the forward direction. Let's try to show the reverse direction. Basically, given 4-point condition, we want to show that delta D is equal to D. And as I said, like we will just use the previous lemma that we already know that like D is bigger than or equal to delta D. So we just need to show this is known from lemma 9 that in the paper. Then or you can see my earlier video for that. And we just need to show, actually therefore we want to show, basically we want to show this. So if we show that we are done. I think I write not the same. Yeah, it should be like this. The lemma 9 is like D is bigger than or equal to delta D. So I want to show this. So if this is true, then we are done. So to show that, like, we need to look at any members from S, right? From the base set S, let's say A and B from S. Pick any of the members here, and let's consider a function f this way. So I define a function fx, and x is basically again some other member in S, and we define fx as dxa minus dxb. So then, like, because of like the triangle inequality, we have like dax is less than or equal to dbx plus dab or dba, and also like I should have like also like dax plus dab is bigger than or equal to dbx. So then I will have basically from this one here, I will have like dab from the first equation, that dab is bigger than or equal to dax minus dbx, and this is just equal to fx. So I have dab fx is less than or equal to dab, and also like from the second equation here I have dax, let's see how should I write this. I guess it's a dbx minus dax is less than or equal to dab, then therefore like minus dab is less than or equal to minus dax, or like I just write dax minus dbx. Right? I just flip the sign for everywhere. So then therefore like this will be bigger than or equal to minus dab. So in conclusion, I have basically fx is less than or equal to dab but bigger than or equal to minus dab. And so then pictorially we will have something like that. We have fx is basically lying in this range here. Let's dab here to from minus dab to dab here, and note that x is a s is a the member set, right? It's a finite set, so therefore it takes discrete values here. So I can have like different member. Maybe I call it this like c1 and c2 here. So like this is like fc1. So I have like the when basically when x here, like this value is actually when x is equal to, this is like f a, right? So this side is fa. When I have x equal to a, then I will have minus dab, right? And when I have x equal to b, then I will have like dab. And in the middle, like for all members in S, so I have like different values here. I have f as a c3 and so on and so forth. Now if I pick like any ci here, like pick any member in the middles, and then let's say I consider two sets here, like for all the member in S such that like fc is less than equal to alpha I. Okay, my alpha I is something I call this is, let's say I call fa as alpha 1 here, and fc1 alpha 2 here, and so on, alpha 3, and so on and so forth, until like alpha s. So let's say I have like s members here, like and so then I can split all the members in S from two sides. Either like they have the values f is like less than some alpha I here, or like it's like for C that is bigger than some alpha I plus 1 here. Actually I don't need that, so or maybe it's, I think it's more canonical to I don't know, I can't forget, like, so maybe like why like that looks a little bit better. Yeah, so that would be like two sets. This is exactly a split, right? I can split the set S into this way. So either I have fc is like less than alpha I, or like fc is bigger than alpha I minus 1. And this is like a distinct split, right? And this split will separate basically A from B. Because like, of course, like I have one side, like this one will contain A here, right? This one will contain A here, and this side will contain B here. So it's a split that it's one of these sigmas. This is some kind of sigma that actually will split into two of them. And now what I'm going to do is like I'm trying to I'm going to denote this this kind of like sigma, like this sigma as sigma I here. So like for the I1, I call this like sigma I here, this split as sigma I here. So what I'm going to show is like mu sigma I is bigger than equal to 1/2 alpha I plus 1 minus alpha I. This is what I'm going to show. So, but let's look at the conclusion first. So if I manage to show that this mu sigma I is bigger than this difference here, half of this difference here, what I'm going to get is a delta D AB, the difference between them. So what's delta D is basically sum over mu sigma for all the sigma that delta sigma that AB basically saying that I have sum over all the sigma that separate A from B, right? And of course this will be bigger than the summing over all the mu sigma I here, because like all the sigma here is also separate A from B. Right? I mean omit some of the sigma, but I can include all the sigma here. And then yes, and then like if this one is equal to this guy here, then this will be bigger than equal to 1/2 I equal to 1 s minus 1 alpha I plus 1 minus alpha I here. And then of course this is basically just equal to from FB to FA, right? So it's just equal to actually it's just equal to okay, DAB to minus DAB, so therefore it's just equal to minus 2 DAB, but over 2 is just equal to DAB. So therefore we will have delta D is bigger than equal to D as what we want. So now the only thing left behind is that we need to show this one. For convenience, I will just relabel like the symbol here. I will just instead of like mu sigma, I will just call mu sigma simply, and then like x I will simply call it like sorry, not x, alpha I plus 1. I will just call it alpha pi, and this alpha here, and let's start a new page for that. So I'm going to show that mu sigma is bigger than equal to 1/2 alpha pi minus alpha, let's say, and remember like what is mu sigma. So mu sigma is something like 1/2 minimum. So I will need to find this like xy ct that in S such that xy separates ct, and the minimum of dxz plus dyt minus dxy minus dct. So I have the sigma that separate xy from ct, and we will just like here we'll assume that, so because this is like arbitrary labels, right? And we'll just say okay, the xyct that actually reach this optimum will be just xyct. So first of all, I assume like this is actually equal to xyct, and also like I will assume that like this is satisfied, fx is less than equal to fy, and less than equal to alpha, less than equal to alpha pi, is bigger than equal to fc, less than equal to ft. So basically like we have the sigma is separating like xy from ct, right? So therefore one should be like on this side, these other ones on this side here. So ct is more like on the b side here, xy is on the a side here, and also like I can just relabel if like turns out like I have x is bigger than y, I just call x as y instead. So therefore, like, I can always assume that I have fy bigger than equal to fx. Similarly, I can assume that fc is bigger than less than equal to ft here. And then with that, then I have fx. That is, again, it's just equal to dax minus dbx here. And similarly, I have fy is equal to day minus dby, and so forth. Then let's say if maybe I write one more, the fc is equal to dac minus dbz, and then since I have like fx is less than, actually strictly less than fz here, so since I have this, I have dax plus dbz is less than like bx plus daz, right? So basically, I just use these two equations that I just move the negative terms to the other side. So and then by 4 points, so we remember that I have this 4-point assumption here. So we assume the 4-point assumption holds, and we want to show delta d is bigger than equal to d, right? So by 4 points, I have like dxz plus dab is less than equal to the maximum of dax plus dbz and dbx plus daz. And note that like from this equation above, I already have like dbx is bigger than equal to dbx plus daz is bigger than dax plus dbz, right? So therefore, I should have this guy is just equal to dbx plus daz. So therefore, I have one equation like this. And I can derive a couple similar equations like in the same manner. Basically, let's say since I have fy is less than ft, and if I also write down ft is equal to dat minus dbt here, then this will give me something like day plus dbt is less than dby plus dat. And then by the same token, I'm using the 4 point, I have like dyt plus dab is less than equal to maximum of day plus dbt and dby plus dat. And again, I use the equation just here, like dby plus dat is bigger than day plus dbt. So therefore, like I will just have this term instead. So it's equal to like dby plus dat. So, and we can continue to do that. Like we can create 4 equations like this. So maybe I'll just give the result immediately. So, or like maybe I put in the how I get this. Basically, like I also have fx less than equal to fy here. So by the assumption here, fx less than equal to fy here. So I have dax plus dby is less than equal to day plus dbx. And then with the same token, using the 4 point, I will have an equation like dxy plus dab and will be less than equal to dy plus dbx. And lastly, again, I use the totally same token. I have an equation that like dab plus dzt is less than equal to dat plus dbz. So now I have this equation here, and this equation here. Oops, it looks like I caught a small bug in the proof, like on the Buneman's paper. So here, like as you see, I have the inequality. Like the first one, I'm trying to use the property that fx is less. Oops. Fx is less than fc, so therefore I have this idea x is less than that here. So then using this 4-point property there, the 4-point, and then I have this one here. This is less than this guy here, and then like this is bigger than that. Therefore it's equal to this one here. But because like the 4-point inequalities is the 4-point condition is like an inequality, I believe. So at least it's what is defined in the paper there. So where's the 4-point there? Yeah, the 4-point condition here is assuming an inequality. So if we assume the inequality, then this is really a less than equal to instead of like equal to, and in the paper there, like yeah, I think this is a minor bug. It's so it say it's equal to, but it's actually less than equal to. But that would be a it would be have a consequence for this minor bug, because then what we are trying to do is we have that for inequality here. That's supposed to be inequality. Then we move the terms like dab like on the other side, as you can see here. Basically, I have dab here. I move to this other side. Therefore, we get this one here. So I think it's supposed to be an inequality, but somehow the Professor Buneman here that I believe is a bug, and and this is an equality. Then what he's trying to do then is trying to show that mu sigma, because mu sigma is given by this guy here, mu sigma plus this guy minus these two guy here. So I can say like this is less, this sum here of this 4 term is less than equal to, or actually bigger than equal to, I substitute this guy here. So what I mean is that I want this thing, mu sigma, this 4 term like dxc dyt minus dxy minus dct, to be bigger than equal to something. So, and because I have a minus sign here, so I substitute, like for example, I substitute dct here, it's okay. So it will be bigger than equal to, if I substitute the right hand side here, dcb plus dta minus dab. However, for these two here, if I also have inequality, I cannot substitute into here, because then I want to be bigger than equal to, but this is less than equal to. I substitute this guy, it won't work. So I guess one possibility is that we actually need to tighten the condition a bit. So the 4-point condition, at least if we just follow the same proof here, if maybe there's some other proof, but from this proof, like we will need the 4-point condition to be equal instead of like less than equal to. We need this guy is exactly equal to this guy, then everything afterward will just hold perfectly. So then we can just substitute these 4 terms here into here, and then I will get loss of cancellation. Eventually, we just get fc plus fy back minus fy back. Basically, fc is like f dac wait a sec dac minus dbc and plus day minus db should be plus dby minus day, something like that. That's 4 terms like that, then we can group them together to fc minus fy. Then because we have the initial assumption that fx is less than equal to fy, less than equal to alpha, less than alpha pi, less than equal fc here, so therefore like fc minus fy will be bigger than alpha pi minus alpha, so therefore we have this one here. So therefore like we will show that like mu sigma bigger than equal to this guy here. So again it looks like there's a small bug in the proof. Either we may need another proof, or like we probably need a little bit stronger condition. Basically the 4-point condition will be like not this guy less than equal to this max there, but at least we need a condition that this is exactly equal to max of this guy here. So if that happens, then we are good. So then let's see. Then of course with that, then with this before we have basically like oops. Yeah, so we have like mu sigma I is bigger than equal to that, and then again like this alpha I plus 1 minus alpha I, if I add all of them together from 1 to s minus 1 s minus 1, then we just get the whole distance like dab to minus dab, so basically 2 dab there over 2, I will get dab back. So therefore I have delta d is bigger than equal to d. And again together with lemma 9, then everything I will also have like the other inequality will have like d is bigger than equal to delta d, so therefore I will have like d is equal to delta d. Again, like the intuition seems reasonable, assuming that like we have this 4-point condition that we described earlier. The 4-point condition is like it's something like if I have for example like this a b c d here, so if I have like for example like ab, distance of ab plus distance of cd, so I will have this guy here and this guy here will be the same basically distance of ac and distance of bd. And of course there's other combination here, there's another term here, but the other term will be smaller with like that the other one is like bc and ad. So and therefore like this is actually equal to that. So it looks like the 4-point condition with equality is kind of like makes sense also. And when your this lateral distance d is like kind of addictive. So and again like when this is addictive to begin with, because the induced addictive metric is supposed to be addictive, so it's like you start with like something already addictive and try to force it to be addictive, it will just become itself, it doesn't change, so therefore you have delta d is equal to d. So anyway, I guess that's my last video for this paper, and I guess we will talk about something else next time.